Hello friends, today we'll discuss an experiment of Planck's constant by radiation. The aim of the experiment is to determine Planck's constant H by measuring radiation in a fixed spectral range. Here we aim at measuring radiation from a black body at different temperatures. The experimental setup consists of a filament bulb with a filter fitted to it. To give supply to the filament, we have a power supply of 12 volt range which is fitted inside this. A photocell fitted on the mini optical bench. To measure the current and voltage of filament, we have an ammeter of range 2 amperes and a voltmeter of 10 volt range. To measure the photocurrent, a digital DC microammeter of 2 microamperes range is connected. As we told that we will be measuring the black body radiation, so let us see first what a black body is. A black body is an idealized physical body that absorbs all the incident radiations regardless of frequency and angle of incidence. The name black body is given because it absorbs all the colors and reflects none. When heated, a black body emits electromagnetic spectrum, which is determined solely by the temperature of the body and not by its shape or composition. A black body is an ideal emitter because it emits most at a given temperature. It is a diffused emitter because it emits in all possible directions. Now let's have a look on the black body radiation curve. This is a curve, the spectral radiance versus wavelength. So black body emits a definite amount of energy for a given temperature, which is represented by the area under the curve. This graph depicts how the black body radiation curve changes at various temperatures. It shows that with increase in temperature, the peak radiance goes on increasing. The black body radiation curve also shows that a black body radiates at every wavelength. But as the temperature increases, the peak wavelength, that is the wavelength at which the peak radiance occurs, decreases. Secondly, as temperature increases, the total energy emitted increases because the total area under the curve increase, though this relationship is not linear. So by putting many restrictions at a given wavelength lambda, the relation between photocurrent theta and absolute temperature capital T is of the following form. After taking log, we can see that this is an equation of a straight line when we plot it for log theta versus 1 upon t with this as the slope of the line. So slope of the line can be used to determine h. This is our actual experimental setup. Now this is the photocell, this is the filter attached to it, this is our filament, and this is the mini optical bench. We have an ammeter here of 2 ampere range, a voltmeter and a digital microammeter. This is a control knob, and before switching on we should ensure that this should be at the minimum position. Now let us take the reading for the just glow position. So we increase the current so that the bulb just starts glowing. There is no photocurrent. At that instant, we take the value of current and the value of voltage to get RG value. This and then we again switch off the system and take the reading at these thrice to get the accurate values. This is for the calculation of just glow position. To take the readings further, we fix the position of the filament bulb and then increase the filament current so that we get some value for the photocurrent as well. As we can see that we get, when the current increases beyond a point, we get the photocurrent also. So we note down the filament current, filament voltage and the photocurrent. Then we increase the current further so that photocurrent voltage changes. We go on taking the readings by changing the filament current, the reading of voltage, photocurrent and the current, filament current. We note it down for a good range of the current. And then for the second set of the reading, we change the distance between the filament and the photocell. Say for initially it was 12 centimeter, now it is kept as 14 centimeter, and then repeat the procedure. That is, by we change the filament current and corresponding changes in filament voltage and photocurrent are measured. Now before switching off the setup, we must ensure that all the knobs are at the minimum position. Now let us see the calculation and observation part of it. So we have noted down these tables. The first table is for the just glow position. So we have noted down the current as well as the voltage. So we can calculate Rg from it. This Rg will be used to calculate RT upon Rg and finally the temperature. For the second set, we fix the distance between the two and then take the V filament voltage current and the photocurrent. So from V and I, we calculate RT, that is the resistance at some temperature, then RT upon Rg, and either by using this table or by using this graph, we calculate the absolute temperature. So for example, if RT upon Rg is 2, we calculate the temperature as this value. So for every RT upon Rg, we calculate T, and with T, we calculate 1 by T. So then we have log theta, we have 1 upon T. We plot this graph, which is a straight line with a negative slope. This slope we calculate from here, from this graph, and is used to calculate the H finally. So this is our formula, as H is this into slope. Slope we have already calculated, so we can find out the H from here. So we can report our result for the Planck constant. The standard value of Planck constant is 6.26 10 to minus 34 joule second. Then let us see what are the different precautions we have to take. So before switching it on the setup, must be ensured that all the knobs are at minimum position. For reading and taking just glow position, we should not leave the setup for a long time because it may heat it up. Experiment should be performed in dark room. And then while determining the temperature, we should take care, and log theta versus 1 upon T graph should be drawn with perfection. Thanks for watching. Have a nice day.